in this session, we give the steps on how to carry out the bisection method for approximating the solution to the equation f of x equals to 0. So these are the steps. So majorly there are 3 main steps, and then we repeat the steps up to the point where we get the desired level of accuracy of the solution. So step 1, start with 2 points. Say XL and XR. Such that if you take the value of the function at XL, you multiply by the value of the function at XR, then it's always less than 0. That's from the theorem that we stated earlier on, that a root exists between 2 values when the value of the function at the endpoints of the interval are having opposite signs. So this is to mean that the solution is lie in the interval XL, XR. Now our notation XL simply means the value of x to the left, and XR just to mean the value of x to the right. So this, we are trying to, if this is y equals to f of x, so this is why we're calling XR, and this will have XL, such that the value of XL, as from this graph of sketch I've drawn, f of XL is negative, while f of XR is positive. So we are always assured, because f of x is assumed to be a continuous function, then there exists a root between XL and XR. So that's the first step. Sometimes you may be given the interval XL, XR, and sometimes you may be required to find the interval on your own. But the key thing to know that the root lies between these 2 values, XL and XR, is to ensure that when you take f of XL times f of XR, you get a negative value, or simply the sign of the solution of f of XL and f of XR are opposite. One positive, another one negative. And does not necessarily mean that f of XL must be negative and f of XR must always be positive. That's really not the case. The thing is that f of XL, when it's negative, then f of XR must be positive, and vice versa. When f of XL is positive, then f of XR must be negative. Step 2. So from these 2 values, one, the first condition is satisfied. Then from the 2 values XL and XR, known to have f of XL times f of XR is less than 0, determine a value say halfway between XL and XR, i.e., this C is obtained by taking XL plus XR, then you divide by 2, simply the midpoint of XL and XR. So that's second step. Now, if I may draw a sketch here to explain. So this x-axis, 0, y. So assuming this is where you have the xl, and this is where you have the xr. So f of xlr is positive, f of xl is negative. So we are assured that we have a solution between xl and xr. So step 3, part 1 of 3, if f of xl and f of c have opposite signs, now if I may use my diagram to explain this point, when we say f of xl and f of xc have opposite sign, then we mean that, so possibly c is at this point here, because already f of xl is negative. So for us to have f of c positive, opposite sign, then it must be positive, and same can be at this point. So this way we'll have now f of c, which is positive. So the sign of f of c and f of xl are opposite. Then the root lies between xl and c. So replace xr by c and repeat step 2. So you see the main objective is to get this value. So at this point, we have the exact root, say alpha. So we have this interval from xl to xr. So our main aim is to do iterations that tries to reduce this distance from xl to xr so that we approach this point alpha. So we are trying to reduce this gap. That's the main objective. So because f of xl and f of c have opposite sign as explained in this part 1, then it means that where there's x, instead of having xr at this point, then it is taken to this point. So we are trying to move closer and closer to this root alpha. But we may find case 2, if f of c and f of xr have opposite signs, then the root lies between c and xr. Now, according to this diagram I've drawn, this is what we mean. That if you say f of c and f of xr have opposite signs, so because already f of xr is positive in this diagram, so it means that c will be somewhere here, so that when I define the value of f of c, then now it will be negative. So therefore, we replace xl by c and repeat step 2. So I remember the key thing is to reduce this gap from xl to xr so that we move closer and closer to this root alpha. So that's why we are doing this one. So, and we know that the solution will be between xl and xr whenever the value of the function at these two extreme points in the interval are opposite or have opposite signs. So number 4, the procedure is repeated until the required is achieved. So that's what you have. The process is repeated, so 1 to 3, until the required accuracy is achieved. So the question will specify the accuracy that your solution should have. And just to make things clear, stopping criteria. So choose a small positive number. Epsilon, and then stop. When the difference between two consecutive iterations, xn and xn plus 1, is less than epsilon, where this epsilon is chosen to be a value 0.5 times 10 raised to the power negative m, where m is the number of decimal places. So really what this condition means is that if, for example, they ask you to round off your answer to nearest 4 decimal places, then you carry out the first iteration to get x0, the initial approximation, and then x1 gives the next iteration, x2, etc. So assuming that x1 you get 0.013467, x1 you get 0.01351123. So at every point, ensure that you round off your iterations to the stated level of accuracy to compare the solutions. Now, for the example, this one will have 0.013 and then 5. And this will give you 0.0135. So assuming this was the case, then you are allowed now to say that the answer to this equation, the answer to the equation you're trying to solve is 0.0135, because the values of consecutive iterations, when rounded off to the level specified, give the same answer. So we'll see the nitty-gritties of that explanation in an example that we are going to do next. So let's do an example in the next session to illustrate how the steps we have stated above applies to approximating solution of f of x equals to 0. Thank you.